Okay, well, I'd like to thank the organizers for inviting me to participate in this very broad-based and interesting conference. My topic today is interstellar water, its history, past, present, and future. The motivation for this talk is the following. For the past 50 years, we have been working to understand how and where molecules form in the interstellar medium. And at the same time, colleagues of ours have been working to detect and amass a growing list of exoplanets and multi-planet exoplanet solar systems. To understand the planet-forming disks that gave rise to these planets requires knowledge from both fields, and in particular, how newly forming planets get their ingredients for life, in particular water, is the subject of interest of my talk today. So the outline of my talk is the following. There'll be four little sections. The early years, which I define as 1969 to 1983. These are the first observations of water and insights into how water forms in the interstellar medium. The second is 1983 to 1985, which gave rise to a number of modeling papers that took the basic mechanisms of water formation and applied them to different molecular clouds and shocked gas regions. And based on their predicted water line strengths, a number of us attempted to actually detect these water lines and verify these models. Something of a golden age was between 1995 and 2013, which saw no less than 6 space missions that had capabilities of detecting water. And it was during this period that water began to yield its secrets. The last part of my talk will be 2020 and beyond. I'll discuss a few new space telescopes that will explore the convergence of astrochemistry, exoplanets, and exobiology. Quick disclaimer though, the limits of time prohibit me from discussing the many pioneering observations using non-water lines such as CO, OH, and H2, among others, that brought clarity to the structure and dynamics of star-forming regions. Those working in labs and on computers to calculate or measure collisional rate coefficients that determine how the chemistry proceeds to form water. The many technologists who helped develop and improve the devices that enabled the observations I'll briefly describe. And lastly, apologies to those whose contributions I lack time to fully mention. So let's start at the beginning. Beyond the water that we almost wallow in on Earth, water moved from the realm of the imagined in space to the real when it was first detected in 1968. The paper came out in 1969 by Charles Towns and his collaborators using the Hat Creek Radio Observatory north of San Francisco, in which they obtained the first detections of what is now the very well-known 22 gigahertz water maser line, which they did towards SAGB-2 and Orion, confirming that water was not just limited to the Earth, but existed in interstellar space. Water was the 6th molecule to be detected. Here I show a histogram showing the number of molecules detected as a function of the decade of discovery. What's striking about this, in addition to the detection of water being the 6th molecule discovered in interstellar space, was that it was among the first to benefit from the advances in radio astronomy, which then produced this explosive growth starting in the decade of the 70s and onward in the detection of different molecules. But at the time of the detection of the 22 gigahertz water line, we had no idea how water formed in interstellar space. That was partially resolved by a foundational paper by Eric Herbst and Bill Klemperer, who laid out a path to forming water in cold gas via what is known as ion neutral reactions. Basically, this scheme starts with a cosmic ray ionization of H2 and proceeds with the reaction of a successive number of neutral and ionic species through to the formation of H3O plus, which is dissociatively combined with electrons in the gas to form water, or OH. The appeal of this network of reactions is that because it involves an ion, it essentially uses the attractive force of a charged particle, which means that these reactions can proceed over a relatively long spatial range and is strong compared to reactions between two neutral species, and it works at low temperatures. In a time scale of 3,000 years to 10,000 years, in gas of 10 to the fourth to 10 to the sixth per cubic centimeter, you can achieve an abundance of water of about 10 to the minus 7 relative to H2. So that's where things stood in 1973. One line detected and one model. There was another detection of a different water transition in 1983 that was presented in a bulletin of the American Astronomical Society, but without any interpretation offered. In 1978, there were two developments. One was based on the chemical scheme outlined by Herbst and Klemperer. Paul Goldsmith and Bill Langer analyzed the cooling potential of a number of different molecules in dense molecular gas. And what they find is shown in this plot in the lower right, where I show cooling power along the y-axis and cloud density along the x-axis. The thing to note, two things to note are in pink is the total cooling at 20 and 40 Kelvin, and in blue is the cooling due to water. And what you'll notice is that at cloud densities of 10 to the fifth and greater, they predict water to be the major gas coolant. Unfortunately, to study gas at 20 to 40 Kelvin, you can only observe the lowest lying energy transitions, which all fall in the far infrared and submillimeter. And unfortunately, these low energy transitions correspond to rather strong atmospheric absorption features in our atmosphere, not surprisingly. Even at the altitude of NASA's SOFIA airborne telescope, the atmospheric transmission is essentially nil at the line center. Here I show an atmospheric transmission plot where 1 is 100% transmissive, 0 is totally opaque, and here you see frequency along the x-axis. And to give a reference, this purple area, this shaded region, covers plus minus 400 kilometers per second, which means that for any cloud within our galaxy, this water line is essentially totally opaque at even 43,000 feet. And if you look at the other low-lying transitions, you get basically the same story. It's just not possible to observe these from an airborne and certainly not any large ground-based facility. So that's where things stood. In 1978, there was an interesting detection made of isotopic water, the transition shown here, which was detected from the ground because isotopic water has an abundance of about 1/500th that of the nominal isotope of water. And therefore, the atmospheric absorption feature around this line at 203 gigahertz is such that you can get a detection toward a strong source, which they did. And interestingly, they derived an abundance of 10 to the minus 5 of water relative to H2. And they noted that this was much larger than the abundance predicted by Herbst and Klemperer. And in the last sentence of their paper, noted that it's possible that water is formed outside of this scheme. In that same year, actually, and I don't think these were coordinated efforts, Elitzer and de Jong published a paper in which they outlined an alternate path to forming water via neutral-neutral reactions in hot gas that would be heated, so they say, by shocks, reasonably so. So you have this situation where oxygen reacts with H2 in hot gas to form OH, and OH reacts with H2 to form water. The advantage of these reactions are that the high temperature overcomes the rather large activation energy, which is an activation energy that cannot be overcome in quiescent molecular gas, but can be in shocks. And they note in their paper, interestingly, that these reactions proceed very quickly. You can see on the right the plot that shows log time and the density of each species. And you see that within about 10 years, as they note, all the oxygen in the pre-shock gas, not in CO, which is a very strong bond and can't be broken in these type of shocks, all the oxygen is driven into water. And it's a relatively high abundance. So the notion that water could be formed in a second pathway behind shocks was bolstered in I think this was 1980, in which Tom Phillips and collaborators obtained a different water line, a normal water line, that was quite wide. And they based their interpretation on the de Jong and Elitzer model, and noted that they are deriving a water abundance of 10 to the minus 5, 100 times greater than the cold gas method of producing water. And they associated it with shocked gas in Orion based on the width of the line and the direction toward which the detection was made, which also corresponded to very strong rotational H2 emission, which was also attributed to shocked gas. In 1980, there was a refinement of the shock models that was very important. And I'm mentioning it because this was essentially a new type of shock at that time. This is a shock with a magnetic precursor that basically softens the shock, and you get heating with the magnetic field dragging the charged particles, the electrons and protons, can stream through the neutral gas, which is unaffected by the magnetic precursor, which heats the gas rather gently. That is to say, there are no discontinuities in the shock hydrodynamic variables. So essentially, you get the heating of the pre-shock molecules without their destruction. Now, whether this model actually is borne out in nature was tested by predictions by two groups in back-to-back papers in 1982, in which they sought to explain existing observations of molecular oxygen, CO, and OH, and they found that these models did an excellent job of accounting for the flux of these species, but it had an interesting additional prediction, and it applied that water, which up to that point had only been observed in one line toward one line of sight, should be very highly abundant, about 10 to the minus 4 relative to H2. Moreover, they predicted that water is a major gas coolant in the shocked gas, and in fact that it dominates all other coolants in dense gas. By dense, I mean about 10 to the 6th per cubic centimeter. So by 1983, we knew there was water in the ISM. We had two very viable models for how that water formed. The model suggested that water would be a major gas coolant, and shock gas models predicted very high water abundances. So in 1983, we knew, unlike in 1967, that water was not only familiar to us, but that it was present in the ISM, and not only that, it plays an important role in the ISM. What we didn't have at that time was a clear idea of which lines to target and how to observe them. So now we move to 1983 to 1995. One of the more interesting papers during that period was a paper by Takahashi, Hollenbach, and Silk, in which they examined in detail the water spectrum from a dense, cold molecular cloud. It made very specific predictions, but unfortunately for observers, all of these lines are relatively low excitation lines, as you would expect in a cloud that's cold, and therefore correspond to rather strong atmospheric features. So we knew that in order to test any of these models, we needed to get above the atmosphere. Around the same time, David Neufeld and I took a different approach. We thought, well, let's see under what conditions we might have weaker atmospheric water lines. So we modeled shocked gas water emission in order to see if we could detect any of the higher lying water lines from a shocked gas region whose corresponding atmospheric feature was not that strong. As a byproduct of this investigation, we found that the total flux in all the 4IR water lines accounted for about 40% of the total power input into the shock. And as I say, we hope to find a few of these lines that had weak atmospheric counterparts. So the first thing we did was apply for time on NASA's Kuiper Airborne Observatory, in which we targeted a number of lines that were between 3,000 and 4,000 degrees Kelvin, which we believed would have weak atmospheric counterparts. We chose a time of the year when Orion, the canonical best source to observe any molecular line toward, had its maximum Doppler shift, which is in spring. You see this in the plot on the left side, where it's month of year and the velocity of Orion relative to an observatory on Earth. And on the right side, you see two different atmospheric transmission plots showing a weak atmospheric feature. They're weak because they're very high excitation, and how the Doppler shift of Orion at the right time of year can move the Orion line away from the atmospheric line. Unfortunately, we were not able to detect these very high excitation lines, which were also weak in Orion. So this led us to conclude we needed to go higher. So in 1987, we decided to combine an existing 1 meter diameter balloon-borne telescope that we had at the Center for Astrophysics with an existing balloon-borne far-infrared spectrometer built and operated by University College London that had previously flown successfully on one of their balloon payloads. Again, we targeted Orion. And again, the optimal time was in the March-April timeframe. But now, because of the higher altitude, we were able to target a lower excitation line, in this case about 1200 degrees Kelvin. And you see the 50 kilometer per second Doppler shift, near 100% transmission. Our window for observing Orion lasted until April 4th. Windy conditions prohibited a launch any sooner than April 2nd, which was near the edge of the window. As a result, when we got to altitude, Orion was only 15 degrees above the horizon. And while we detected something suggestive of the line, here it is in two different orders of the spectrometer where we expected the line, it's evident that the noise is such that we could probably only claim a 1.5 to 2 sigma detection. So our conclusion was we needed to get higher still. We needed to go to space. So now we're at the dawn of the space age. A number of missions had been proposed in the late 80s and were coming to fruition starting in the 1990s. Here I show 6, as I mentioned earlier, that have a bearing on water. I was the principal investigator for the submillimeter wave astronomy satellite, the deputy PI for one of the 3 instruments on Spitzer, and a co-investigator on the heterodyne instrument that was flown on Herschel. So much has been learned from each of these missions that entire conferences have been dedicated to each of these missions. But if I had to summarize their collective results by standing on one foot, I would say, 1, outflow shocks do rapidly and effectively elevate the water abundance, though not quite as much as we initially expected, to which we attribute that to the fact that ambient far ultraviolet radiation prevents the full conversion of oxygen into water. Water may be formed, but it's also partially photodissociated by the UV fields, in this case associated with the protostar at the center of this outflow. We find that within quiescent dense molecular clouds, water exists, but predominantly near the surface of these clouds rather than the interiors. Here I show a map I made along with my group using the heterodyne instrument on Herschel of the ground state water line toward the Orion molecular ridge. And we compared this to the strength and distribution of 7 other molecular species, and could show rather convincingly that the water emission was much more closely associated and correlated with molecules that we know to be surface tracers rather than volume tracers like CO, for which water did not correlate well. Finally, we've learned that deeper into the clouds, water exists as layers of ice on dust grains. This is the least tested of the 3 mechanisms, but I'll get to that. This mechanism is basically very simple. Dust grains are constantly colliding with atoms and other molecules in the gas phase. In this case, collisions with hydrogen, which is the dominant species in these clouds, is very frequent. And when an oxygen atom hits the grain, these atoms can migrate rather effectively over the surface of the grain, find each other and react and form water on the grain. So now we've rounded out 3 different routes for forming water: the low temperature, the high temperature, and the ice path toward getting to water. With regard to the surface nature of water, I refer to this cartoon of a molecular cloud where the x-axis is distance into the cloud measured by visual magnitudes, and the y-axis is the gas phase water abundance. Near the surface of the cloud, the water abundance is relatively low because any water formed in the gas phase or on grains, in the case of grains, it's photodesorbed rather quickly, and once in the gas phase, it is photodestroyed. Deeper into the cloud, the far UV field is attenuated, and you get a balance between molecule formation in the gas phase and on grains, and desorption and destruction. And there's where you see the peak of around 10 to the minus 7 relative to hydrogen. Deeper into the cloud, that is to say beyond about 8 magnitudes of extinction, the far UV field is essentially negligible, and any molecules that form on the surface of grains or in the gas that freeze out on the grains will remain on the grain. It's too cold in these clouds at that depth to photodesorb or thermally desorb these molecules. So in 2009, we modeled all of these processes, the photodissociation, photodesorption, photodestruction, We came up with these plots which show depth into the cloud and the abundance in this case, of water, both the gas phase and ice, as a function of depth into the cloud. This factor G naught is just a simple scaling factor times the strength of the far UV field in the solar nebula. And the takeaways from this are that as you rheostat up the far UV field, the peak of the water abundance moves deeper into the cloud, not surprisingly for a fixed density. If you fix the strength of the far UV field and increase the gas density shown in the right panel, as the gas density increases, not surprisingly, you attenuate the far UV field closer to the surface of the cloud, and therefore the peak in the water emission is closer to the surface of the cloud. But the headline of this story is the following, that in all of these cases, the abundance of the ice is almost 1,000 times greater than the abundance of water in the gas phase. So we find that more than 99% of the water in the interstellar medium, we predict, is locked in ice. And so there's a common mantra within NASA, which is to find life, follow the water. I think it should read to find life, follow the ice. So in conclusion of this section, some combination of these three mechanisms can explain virtually every source detected by these 6 missions, every water source from dense starless clouds to protoplanetary disks. So the challenge going forward is understanding the evolution of water, both in the gas phase and in ice, from dense clouds to protoplanetary disks to planets. So the last part of my talk is a quick summary of 3 space missions that we can look forward to, 2 of them in the near future, one we hope within about 15 years. They are the James Webb Space Telescope, Spherex, and Origins. Starting with JWST, which we hope will be launched in less than a year from now, I would call your attention to the advances that JWST represents. Here is a plot of line flux sensitivity on the y-axis and wavelength on the x-axis, and a number of missions that operate or have operated, and in JWST case will operate in the infrared. The key takeaways are that JWST will be about 10,000 times more sensitive to line emission than ISO, about 100 times more sensitive than NASA's SOFIA Airborne Telescope, and 10 to 50 times as sensitive as Spitzer. In the case of water, this wavelength range permits JWST to have access to a number of ground rotational and vibrational transition of water in their isotopologues, which will probe warm to hot gas. It will have access to all of the low rotational transitions of H2, which can be used to better characterize the physical conditions in outflows from which Herschel and some of these other missions measured shock-excited water. As I mentioned, JWST can measure hot water in the inner regions of protoplanetary disks, and it also has a wavelength coverage that allows it to measure ice absorption spectra, including water features at 3, 4.5, 6, and 13.3 microns. But I will add that being a large observatory, JWST is not efficient at surveying. So the number of ice spectra expected from JWST probably numbers in the few hundred. And I suspect Tom Green will have more to say about JWST in his talk after the networking break. The second mission I'll mention is Spherex. This is an all-sky spectral survey telescope with wavelength coverage between 0.75 and 5 microns, which is scheduled to launch in 2024. We expect that Spherex will obtain millions of ice spectra. There are 3 major science themes for Spherex. One is cosmological, measuring non-Gaussianity, for which Jamie Bach at Caltech is the lead. On the right side is measuring the history of galaxy formation using extended background light, for which Asantha Correa at University of California, Irvine is the lead, and surveying the Milky Way in ice, for which I am the lead. Spherex will be in a sun-synchronous orbit. It will build up spectra as it crosses the sky on successive orbits. It will carry 6 Hawaii 2RG infrared array detectors. Essentially, these are the same detectors as will fly on JWST. The telescope is passively cooled to less than 80 degrees and the detectors to less than 55 degrees Kelvin. And during its baseline 2-year mission, we hope to obtain 4 totally independent all-sky surveys and obtain about 13.7 billion positions, each with a 0.75 to 5 micron spectrum over the whole sky. There are no expendables on Spherex, so it could go beyond 2 years. Just briefly, Spherex will contain a 20-centimeter telescope. As I say, it's passively cooled to the natural background. The spectral resolving powers over this wavelength range from 35 to 130, and I'll explain the differences in a moment. It has a very large field of view, 3.5 by 11.3 degrees, and each point on the sky will have a spatial resolution of 6.2 arc seconds. Spectral dispersion is done using something called a linear variable filter. These have flown in space before. It's a very lightweight spectrometer, 28 grams, and basically the wavelengths vary with position across this piece of specially made glass. The sensitivity of Spherex will be such that we will be able to obtain a high signal-to-noise spectrum for every 2-mass source. We can go at least 4 magnitudes deeper than 2-mass went, and we should obtain a solid detection of even the faintest NASA WISE mission point sources. I'll remind you that the wavelength region between 2.5 and 5 microns is particularly rich for the study of ices. This is an ISO spectrum toward the galactic star-forming region W3A, and here I denote 3 of the 6 bands, wavelength bands in Spherex, and their spectral resolving power. And the spectral resolving powers were selected to allow us to spectrally isolate each of these features. But because they're basically broad solid state features as opposed to narrow gas phase features, you can get by with modest spectral resolving power. That's shown here. The underlying curves in this 6-panel montage are spectra obtained by ISO, and overlaid on them is a convolved to the Spherex spectral resolving power spectra of 35, 110, and 130. And you can see that we basically cover the black curve, which is the R equals 700 spectra obtained by ISO. Spherex will increase the number of high quality ice absorption spectra known by at least 100-fold, from about 200 at present to at least 20,000, and possibly as many as 4 million. This plot shows a different way of representing what we can do scientifically. The x-axis is depth into the cloud. The y-axis is the measured column density of different ices. In this case, water, CO, carbon dioxide, and methanol. And on the left side, you see the range over which we expect to be able to detect these different molecular ices with Spherex. I'll note that where each of these fits of the existing ice spectra cross the x-axis is essentially where these ices begin to form. In other words, where you begin to get greater than 0 column density denotes where these ices form in terms of the depth into the cloud. And if you just compare the y-axis values at a given depth into the cloud, you get the relative abundance of these different ices. So by sampling orders of magnitude more lines of sight, we'll get the depths at which these ices form, as I say, and their relative abundances. And by sampling so many millions of regions at different evolutionary stages, from diffuse clouds to protoplanetary disks, we will be able to determine how ices evolve as they progress from these diffuse clouds to disks. Further, because Spherex and JWST will be operational at the same time, the sources, the millions of sources we detect with Spherex can be examined to extract some of the most interesting sources for follow-up with JWST. As I noted, JWST is not a survey instrument, but Spherex will serve this purpose quite well. However, JWST's exquisite sensitivity, being a 6-meter telescope versus a 20-centimeter telescope, and its broad wavelength range makes it an ideal instrument and observatory to follow up the most interesting Spherex sources. I'll close my talk by mentioning something that David Leisowitz spoke about yesterday. This is a mission concept that is under consideration by the U.S. Decadal Survey Committee. This would be a flagship mission, NASA's most ambitious mission for the decade of the 2030s. I'll remind you, as David noted yesterday, Origins would be 1,000 times more sensitive than any infrared observatory flown previously. It's a 5.9 meter non-deployed mechanical cooler-cooled aperture to 4.5 Kelvin, giving it a natural background sensitivity, and it will cover 3 orders of magnitude in wavelength range, from about 2.5 to almost 600 microns, with a launch no earlier than 2035. The one slide on this mission, and this is the last mission I'll discuss, I think is quite telling as it pertains to water. These 3 panels show bins of the number of water transitions with energies above the ground state in bins of 200 Kelvin, from 0 to 1,000 Kelvin. JWST only has access to 1 water line with an energy above the ground state less than 1,000 Kelvin. Likewise, ALMA only has access to 3 detectable water lines below 1,000 Kelvin, whereas Origins would have access to over 200 water transitions in this wavelength range, which basically makes it an ideal observatory for studying the water trail from protostars to protoplanetary disks, debris disks, and emerging solar systems. So I hope I've convinced you that we've come a long way in 50 years from the first detection of the now famous 22 gigahertz water maser line to mapping water in outflows and in large, massive star-forming regions. And I think the future for the study of water looks extremely promising. So I thank you for your attention.